measurement of magnetic force on a current carrying wire. In this experiment, to investigate the variable that affects the magnitude and direction of the force of magnetic field on a current carrying wire. Theory. A current carrying wire in a magnetic field experiences force that is usually referred to as a magnetic force. The magnitude and direction of this force depend on four variables: the magnitude and direction of the current, I, the strength of the magnitude field, P, the length of the wire, L, and the angle between the field and the wire, theta. This magnetic force can be described mathematically by the vector cross product.
A wire that carries a current, and as you know from our classes, this force is calculated from the formula I L B sine theta, where F is the force, I is the current, L is the length of the wire, B is the strength of the magnetic field, and theta is the angle between the current and the magnetic field directions. Now in this experiment, in the entire of this experiment, we will use theta equal 90 degrees, which means I will put the wire always such that the wire makes 90 degrees with the magnetic field, and in this case sine theta will be always 1. So in this experiment our formula is going to be ILB, and sine theta equals 1. This experiment consists of 4 parts. Part number 4 will be skipped, so we will not do part number 4. We will do 3 parts. So in the first part, part 1, we will investigate the relation between the force and the current, the force and the current. So we will use something like this. We will use a fixed length of the wire, fixed value, and we will use a fixed value of the magnetic field, but we will use different values of the current and make something like this. Several values of the current 1, 2, 3, 4, and for each current we will measure what is the force in newtons. Then we will make a graph. We will put the force on the y-axis, the current on the x-axis, and make a graph. And according to this formula, F equals LBI, this looks like y equals mx. So I expect this to be, when I put F on the y-axis and I on the x-axis, I expect this to be a straight line, and the slope of this straight line must equal L times B, the length of the wire times the value of the magnetic field. This is the first part of this experiment. Now in the second part of this experiment, we will investigate the relation between the force and the length of the wire. So we will use a fixed value of the current and fixed value of the magnetic field. Then we will use several lengths. We will use different wires of several lengths, and for each length we will measure what is the force. And we'll make another graph. The force on the y-axis, the length of the wire is on the x-axis, and according to this formula, F equals IBL. This is again a straight line. When I use L as the x coordinate and F as the y coordinate, I will get a straight line with a slope that equals IB. Then in the third part of this experiment, this was number 2. Now the third part in this experiment, we will investigate in this relation F equals ILB, we'll investigate the relation between the magnetic field and the force. So we'll use a fixed value of the current and the fixed value of the length, but we will use several values of the magnetic field. And for each magnetic field, we will measure what is the force on the wire. Then we make a third graph. We put the force, this is part 3, we put the force on the y-axis and the magnetic field on the x-axis. And according to this formula, F equals ILB, we used F as the y, and we used B as the x, so it will be straight line of a slope that equals IL. So it will be straight line, its slope must equal IL. So this is the theoretical part of what we are going to do in this experiment. Now I will show you how to do the experimental part. So this is the magnet. This is the magnet we are going to use in this experiment. The red part is the North Pole, while the white part is the South Pole. And there's an opening here between the North and the South to put the wire in between. And as we know, the magnetic field must be from North to South. So it must go from red to white. This is the direction of the magnetic field. So in this orientation, the magnetic field must be from right to left, which is the negative x-axis. But if I put it like this, it becomes from red to white, which is in the positive x-axis. If the magnet is oriented like this, then the magnetic field is in the positive y-axis from red to white. And in this orientation, it is from red to white, which is the negative y-axis. Now this magnet consists of a fixed part, this part, and there are pieces here, 6 pieces that can be removed or added to change the value of the magnetic field. So we have 6 parts, 6 pieces. I can remove, for example, 1 piece and keep 5 pieces. In this way, the magnetic field becomes less. If I remove another piece, then the magnetic field becomes less and less. If I remove a third, it becomes less and less. So this generates a magnetic field, and we have the ability to change the value of this magnetic field. These are the wires we are going to use in this experiment. We have 4 different lengths. This is the shortest, which is this length. This length is 12 millimeters. Then this is longer. Its length is 22 millimeters. And the third one has a length of 32 millimeters. And the fourth one is 42 millimeters. Now I will show you how to fix these wires inside the magnet and measure the force. Okay, this is the setup we are going to use. This is the power supply. It's still turned off, sorry. And this power supply will supply a current to the wire through these wires. And the wire is mounted here between the poles of the magnet, as you can see. So the current will come from the positive terminal here, then through this part, then down, then through the wire to the right, then up, then back to the battery through this wire. So we know that the current in the lower part of the wire is in this direction, and since the magnetic field is in this direction, like this, so this means the force will be up. So this magnet will push this wire up. Now, as a result of Newton's third law, for each action there's a reaction equal in magnitude and opposite in direction. If the magnet pushes the wire up, the wire must push the magnet down. And when the wire pushes the magnet down, this will increase the mass of the magnet. Of course, the mass of the magnet is the same, but it will increase the reading of the balance. So now the balance reads 162.641 grams. So this is the mass of the magnet when the current is still off. I didn't turn on the power supply. So this is the actual mass. Now when I push down on the magnet like this by finger, of course the reading increases. But we will let the wire push on the magnet down to increase this number. And the difference in the mass represents the force. Okay, so we should record this value, which is the mass of the magnet when the current is still 0. Then we use 5 different currents. This is in part 1. I will turn on the power supply. Now, as you can see, the current is 1 ampere. The reading of the balance becomes 162.929. Now, when I increase the current to 2 amperes, yes, the reading of the balance becomes 163.216. Now when I increase the current to 3 amperes, the reading of the balance becomes 163.498. And when I go to 4 amperes, now the new reading of the balance is 163.785. When I increase the current again, finally to 5 amperes, this is the final reading, I can see that the reading of the balance becomes 164.079. So this is the end of part 1, in which we used all 6 pieces of the magnet. No piece is removed, and I used the longest wire, which is the 42 millimeters long. So these are the values I will put in the table, and I will give you a photo of the table at the end of this video. So I will go now to part 2. So in this second part, we will do the following. We will change the wires. So I can remove this wire and I can put another wire. Then I put this inside the magnet again. So I will show you what will be the reading of the balance when I use the 12 millimeters and 22 and 32 and 42 millimeters. Through this entire part, I'm using the 6 parts of the magnet, and I will fix the current always to 5 amperes. So the current will be always fixed at 5 amperes. So of course the reading of the balance when the current is 0 is still like the old part, which is 162.641 grams, because I'm still using the same magnet. Now I am using a current of 5 amperes, and I am using the shortest wire, which is 12 millimeters long. This is the reading of the balance in this case. It is 163.017 grams. Okay, now I will go to the next wire. So for the next wire of length 22 millimeters, the new reading of the balance is 163.346, and I'm still using the 5 amperes with the 6 pieces of the magnet. So this is the new value. Now I will go to the third wire. Okay, I replaced the wire. I placed now the 32 millimeters long with 6 pieces with 5 amperes current. The new reading of the balance is 163.704. And the fourth reading and final reading now. So this is the fourth reading using the 42 millimeters long and 5 amperes current. So now we have 4 different lengths and the value of the mass for each of these 4 lengths. This is the end of part 2. Okay, now we come to the third part of this experiment, in which we will change the number of pieces mounted on the magnet. In this part, in fact, since we will add pieces, I will start with 1 piece, then I will add the second piece, then I will add the third piece, the fourth piece, the fifth, and the sixth piece. In this case, we must measure the mass of the magnet twice. Every time I must measure what is the mass of the magnet before I turn on the current, and what is the mass of the magnet after I turn on the current. Because we add pieces to the magnet, so even its actual mass without the current becomes different. So I will start with the first reading when I put only 1 piece in the magnet. 1 piece is now placed in the magnet. I'm still using the wire of 42 millimeters, and the current is now off. The reading of the balance is 97.476. And now when I turn the current on using 5 amperes, the new reading of the balance is 97.740. Now I will mount the second piece. The second piece is now mounted. This is the reading 110.103 when the current is 0. Now I will turn on the current, still 5 amperes. The new reading is 110.653. The third piece will be mounted now. Okay, 3 pieces are placed. When the current is off, the reading of the balance is 122.898, and when I turn the current on at 5 amperes, the reading of the balance is 123.669. Okay, let's go for the fourth piece. 4 pieces are now mounted, and when the current is 0, the reading of the balance is 135.656, and when I turn the current on 5 amperes, the reading is 136.654. I will add a 5th piece now. 5 pieces. The current is 0. The reading is 148.207. When I turn on the current, it becomes 149.381 using 5 amperes. And finally, I will use 6 pieces now. Okay, all the 6 pieces are there. The current is 0. The reading is 162.754. And when I turn on the current, you see the reading becomes 164.117. So I used all the 6 pieces now. This is the end of the experiment. Now I will show you the data in the tables. Okay, this is the data for part 1. We have used 5 currents, 1, 2, 3, 4, 5, and these are the masses we measured at each current. Now the net mass means we must subtract this mass minus the mass without a current to get the value of the increase in the mass. Now this change in the mass must be converted into a force. How to convert this mass into a force? First of all, this mass is given in grams, so we must divide this value by 1,000 to convert to kilometers. Then we multiply the result by 9.8 to become a weight. which is a force. So first of all, every reading of these 5 readings, we must subtract 162.641 to get the net mass. Then this net mass divided by 1000 multiplied by 9.8 will give you the force. For the second part, we will do something similar, because in this second part, this is the table, this is the data we have, 6 pieces are used, 5 amperes. This is the mass without a current, and for each of the 4 lengths, this is the mass we have measured. So we need to calculate the net mass, subtract this minus the mass without a current, this is the net mass, then divide this net mass by 1000, multiply it by 9.8, it becomes a force. Okay, now the third table. Okay, this is the third and last table. We used the 42 millimeters long and the 5 amperes, and we used 1, 2, 3, 4, 5, 6 pieces. I'm so sorry, by mistake I started from the second line, but you should start from the first line. So what is written in the second line must be in the first line. This is why I used the 6 pieces here outside the table. This was just a mistake. Just write them in their correct places. Now in this part, in every reading we must subtract. So for example here we must subtract 97.740 minus 97.476. This is the net mass divided by 1000 times 9.8. This becomes the force. The second reading we do the same and the same and the same and the same until we do this for all the readings. And this is the end of this experiment, and I hope it was clear. Thank you.